Hi friends, welcome to our channel. In this video, we will talk about one of the most powerful ideas in calculus, the Taylor series. Here, you will learn what it is, where it comes from, how it works through clear examples, and why it plays a critical role in science and engineering. Let's begin. Here is what we covered, what Taylor series is, some key definitions, and some examples. Okay, first of all, what is Taylor series? So a Taylor series is a way that allows us to approximate a complex functions using a polynomial. It does this by building the polynomial from the function's derivative or evaluate it at a single point. Why does it work? Within a certain range, called the radius of convergence, added higher order terms to make the polynomial closer and closer to the original functions. And why does it matter? Because polynomials are easy to compute, analyze, and use in modeling across mathematics, physics, and engineering. Now, let's talk about the history of Taylor series. The Taylor series doesn't appear overnight. Let's talk about it. First, the Isaac Newton developed early series methods in late 1660s. And then James Cauchy expanded power series techniques in 67s. These methods was essential before the modern calculus was fully developed. Finally, in the early 1700s, Brooks-Taylor formalized these general expansions that now bear his name. These evolutions made a major milestone in mathematical analysis. Okay, now let's talk about the formula. The formula of the Taylor series is written as this infinity term. You mean the term is super complex, right? Well, let's talk about it in basics. So basically, it sums every terms of the nth derivative at the period 8 divided by the nth factorial times by s minus the period to the power of n. Yeah, I know, you may hate it, right? Don't worry, let's look at an example. First, let's look at a very special number, e. Why this number is super special? Because the derivative of this one, like dy over ds, equals to a des over ds, is still es, is still y. So regardless of how many derivatives, the result will be still the same. And let's use s is 0 as the pivot. Okay, so let's see what happens. So you see the functions at zeros, f0 is 1. Why? Because any numbers to the power of 0 is 1. Indeed, we will know that the derivative, regardless of how many derivatives, at the point 0 is always 1. Okay, let's keep going. So the first derivative is 1, the second is 1, the third is 1, and so on, and so on. So this is the sums. Okay, we can show you the sum again. So because Ex is equal to sigma n is 0. So this is infinity. So f prime 0 as to n over n factorial. And this term is always 1. So we don't have to care about it. So we just place the number here from 0 to very large. So at the 0 is 1. If it's 1 is x. If it's 2, so it's s squared over the 2 factorial. If s is 3, so it's s cubed over 3 factorial. And so on, and so on, and so on. Okay, so now let's look at an example online to see how does it work. Let's visualize how different degrees of Taylor series will approach the result. First, let's put the original expression, which is y is equal to e to the power of s. Next, we will put the Taylor series with different degrees. We first start with 0 degree. Oh, it's a straight line. It's super far from the true functions. Don't worry. Let's put it in degree 1. So we plot as here. Well, it's a line. It looks better, but it's still quite far from the truth. Let's keep going and keep going. So s squared over 2 factorial. Well, it's a quadratic. It's better, but it's still a little bit far. So we keep going and keep going. So okay, now we have 6 terms. It's already close enough, right? Particularly for the positive part. You see the blue and the red part curve, they are super close after the point of -2. And if you show here, you see that, right? So to approach the truth more for negative, all we need is just to add more terms. So it's well, some people may say, what happens if we need 100, 10, 20, or 100 terms? That is, we may need a programming to solve it. Now, let's just use the Pythons. Yes, if you don't know the Pythons, it doesn't matter, right? So, because we will not talk about Python in depth in this video. What we have is we have these degrees, and then we plot the differences between the e to the power, the actual functions, and the approximations. Let's see. So here is the different approximations. You see the 10th degrees is super close to the true functions. But and there are 7 degrees, 5 degrees, 3 degrees, 2 degrees, and 1 degrees, which corresponds to different colors. You see the higher the degrees, the closer to the function. Now let's just change this 15 to a very large, like a 50. No, not 50, like a 40, and see what happens. Let's just change it. Let's just oh, there's an error. Okay, for the 40 degrees, is you see, is super close to the true functions. Okay, so yeah, this is exactly how the Taylor series work for e to the power of s. Indeed, Taylor series applies for other functions. For example, sin s equals to that. So let's just write it formally. So sin s equals s minus s cubed over 3 factorial plus s5 over 5 factorial minus s7 over 7 factorial, and so on and so on. So if we sum it, so its n is 0, infinity, minus 1, 2m plus 1. So 2m plus 1 factorial, and s to 2m plus 1. Oh, I think here is n. Yep, you can plug in and verify it. Okay, so that's sin s. Now let's erase it and talk about other functions. So cosine s and long 1 plus is are as listed. So let's just write them formally. So cosine s equals to 1 minus s squared over 2 factorial plus s4 over 4 factorial minus s6 over 6 factorial equals to the sum of n0 infinities minus 1s and ms2m and 2m factorial, and long 1 plus x equals to 1 x minus s squared over 2 factorial s cubed over 3 factorial, and so on and so on. So you sum as n is zeros infinities. So minus 1 n plus 1 Sn over n factorial. Okay, so that's the Taylor series for these 3 famous functions. Regardless of which one we choose, as long as we have enough terms, the error will be super small. Okay, now let's talk about the applications of a Taylor series. Yeah, some people may think, well, I don't know how useful it is. Well, the first thing is numerical methods. It allows us to expand the approximations using these polynomials. Let's show you some examples. For example, if we need to expand if cube, well, it's a nightmare, right? But if we calculate it as a polynomials, like we plug 3 into x, we can just say if cube is 1 plus 3 squared over 2 factorial plus 3 cube over 3 factorial. So this one will returns to this one, and these are polynomials. They just involve addition, subtraction, multiplication, and division, which is super easy for calculators or computer to compute it. Another part is control and modeling. It's it linearizes the non-linear behaviors. Finally, in signals and physics, they support waveform analysis and field simulations. Well, it's a little bit complicated, but you don't have to worry about it too much. Besides, more than 90% of scientific softwares relies on the functions approximation techniques like Taylor series to power the technology in different domains like engineering, GPS, robots, and even machine learning. So yeah, that's Taylor series. It's a good way to approximate complex functions using polynomials grounded in derivative and local behaviors. It's a fundamental idea that connects theory to real-world computations, and it's still and it's and it remains essential to date. I hope you enjoyed this video. If so, please like these videos and subscribe to the channel. Thank you and see you next time.